Welcome everybody to a new discussion. Today I'm talking to Eberhard Klempt regarding 50 years of quantum chromodynamics. Eberhard was kind enough to put together a comprehensive presentation for this topic, so he will be presenting the history of QCD from the inception until today. I hope you enjoy that.
Yeah, I will talk to you about 50 years of QCD. QCD is an acronym and means quantum chromodynamic and has been formulated along with quantum electrodynamics. Electrodynamic, you may know, this is the theory of the electricity and magnetism, and quantum electrodynamics means that quantum fluctuations are included. The quantum theory was developed in the beginning of the last century and is an important constraint for all physical theories. Quantum chromodynamics is the theory of the quantum theory of particles which have color, therefore chromo, and in the course of the time I will explain to you what color means in this respect. In any case, quantum chromodynamics is the theory of the strong interaction. You know gravitation, as you know electric forces and magnetic forces. These are inside atoms, and quantum and the strong forces hold the nucleus together. So these are very strong forces in comparison to electric forces. This theory, quantum chromodynamics, was invented or created about 50 years ago, in 1972 to 1973. In 2021, I wrote an article on blue balls, and that is a funny prediction of QCD, and maybe we come to it later. Blue balls are my special interest, so I will start with a short commercial. Don't be afraid, it won't be too long. There are many publications on blue balls. In the literature, I found 1,550 publications that have the name blue ball in the title. There are more articles where these are mentioned. And there are so many publications discuss blue balls. And then I was very proud that after many years of unsuccessful searches, we had identified the first blue ball. Clearly, for us, this was a great event, and it had some unexpected properties, and our interpretation met with some reservation, just as a warning. When writing this publication, I scanned the literature to find when the first blue ball was mentioned. And this was in 1972 at a conference in Fermilab in Chicago, where Harald Fritsch and Murray Gell-Mann formulated for the first time the principles of quantum chromodynamics. Then our paper was accepted and published, and then I thought, 50 years of QCD, that needs to be celebrated. And we should write a review article on all what has been done, or at least part of it. I'm experimentalist, and I knew I cannot cover the theory, so I asked a colleague, Franz Gross, from the Thomas Jefferson Laboratory in Virginia, United States. He was a theory division leader in there, and I asked him if he would join to edit such a volume. And he was very enthusiastic, and then we proposed this to the so-called European Journal of Physics. This is a periodical, and they accepted, and So we asked conveners and authors, and on the next slide you see that there are many, many authors, 99 authors in total, and many subjects. In the next slide this continues, and you see that covers an enormous wide range of physics. There are about 60 contributions, and contributions partly from well-known physicists, partly from young shooting stars. And the contents range from historical reminiscences to explorations to theory and experiments. So I would like to go back a bit and look how the historical development was, which finally resulted in quantum chromodynamics.
Mhm.
After the First World War, only very few particles were known. The electrons were discovered next, please. The electron was discovered by Thomson, end of the 19th century. The proton was discovered in 1917 by Rutherford. The neutron, 1932 by Chadwick, and the positron, the antiparticle of the electron, was predicted in 1929 by Dirac and discovered also in 1932 by Anderson. So that was the number of particles, very few, which were known approximately 1944. And then suddenly the number of particles increased enormously. The pion, kaon, lambda, delta, and what's their name is, many, many more were discovered. Next, please. The technique at that time were bubble chambers, where paths could be made visible. These are tracks of particles which come from out of the atmosphere. These are high energy particles which traverse the universe, and then they bang here onto the Earth, and some of them interact in such a bubble chamber, and here one can find new particles.
Just one question on this. What is roughly the scale that we're looking at here? So this cross-section, largely what area does it cover?
These are a typical bubble chamber. At the beginning, they had 30 centimeter. So this is likely some which had 30 centimeter. Later, they had 2 meter or even larger. Mm-hmm. And the tracks you see here, these are the path of charged particles which ionize and then make small bubbles in this bubble chamber, and these are photographically then there were photos and taken pictures, and then later these pictures are evaluated, and then you see here, for instance, you see a kink. I can show this only on my screen, but you see sometimes that there is a particle and then small circles. These are electrons or positrons. This is a way how, for instance, the positron was discovered, that there are right-way particles and left-turning particles. Next slide. In Willis Lamp got the Nobel Prize in 1955 for his precision experiment on the hydrogen atom. And when he gave the Nobel Prize lecture, he said he had heard it said that the finder of a new elementary particle used to be rewarded by the Nobel Prize. But such a discovery ought now to be punished by a $10,000 fine. There were too many particles and people didn't know what to do with this. Today, a few hundred or several hundred short-lived particles are known. To provide you with a feeling how short-lived these are, in a millisecond is the thousandth part of a second. And the lifetime of these short-lived particles is so short that the number of lifetimes in a millisecond is the same as the number of milliseconds in the lifetime of the universe. It's a huge number. So these particles are extremely short-lived, and it needs very special techniques to detect them, to find them. But as I mentioned, now there are many, many known of these. But then is the question, so many particles, how can we understand them? Can they all be elementary? That it was clear they need to be bound by strong interactions because they are so short-lived. But can we understand strong interactions? At that time, gravitational interactions were known. Gravitation is responsible for the Earth circling around the Sun and for the apple falling down on Earth. The electromagnetic interaction was known, which you know from electric light, and the magnetism from magnetic needles. And the weak interaction was known. The weak interaction is responsible for rare decays of nuclei and is very important in burning hydrogen to helium in the sun. So these interactions were known, and these were described by fields. There's a gravitational field and an electromagnetic field, and the weak interactions are also described by fields. So are there the electromagnetic and the weak interaction were combined into electroweak interaction by two famous physicists, Steve Weinberg and Abdus Salam. Can I have the next slide? Weinberg was born into a Jewish family, but he was not religious. He considered religion as an insult to human dignity. But in a talk, he quoted a sentence from the Bible. Abdus Salam is a Muslim, was sitting in the audience, and he interrupted him and said, "This sentence is also in the Quran." Weinberg's answer was, "But we published first." Publishing first is, of course, very important in science. The gravitational and electroweak interactions are very successfully described by so-called field theories. So there was the question, are the strong interaction also provided by a field? Is there a strong field? Next slide, please. Already in 1932, the Japanese physicist Hideki Yukawa suggested a field model for the strong interaction. For this, he needed to postulate a new particle called pion. And indeed, 13 years later, this particle was discovered. So that was a success, and some aspects of the strong interactions could be understood, but the Yukawa interaction, how it is called, failed when applied to understand the many new particles. So that was not the full theory. So many particles in this cannot be. So there are many atoms, and we know why. They consist of protons and neutrons and electrons, and the electrons can be kicked out of an atom. Atoms can be ionized. The nuclei can also be disintegrated. When bombarded with other particles, a neutron can come out, or a proton can come out, or a nucleus can break into two parts. So it could be that the proton, the neutron, the carrier of strong interactions, are composed of more elementary particles. So what did physicists do? The same what they did with atoms. They bombarded, but since these are strong interaction, one needs a bigger hammer, higher energy, to kick the proton and to get other particles out. So they went to the largest accelerators, CERN and in the United States, and hammered the proton, but nothing came out. Or more precisely, new particles were created, but these were the particles which were known, and no fragments came out. It was never possible to break a proton into two parts. So no constituents were found. The field theories came out of fashion. The physicists remembered Werner Heisenberg, next slide, who had invented quantum mechanics. He refused to calculate the equation of motion or so of an electron orbiting around the proton. This orbit cannot be observed. He restricted the theory to observable quantities. Physicists then abandoned field theories and turned to formal approaches. Insider call that S-matrix approach. This process had to be, the processes to be studied had to be consistent with formal requirements of the theory, special relativity and theorems derived in function theory. And the increasing number of new particles was used to declare nuclear democracy. All particles are fundamental. All particles can be generated as bound states of each other. Sounds a bit crazy, but that was the theory. This was called bootstrap and reminds of the famous German Baron Münchhausen. He was once riding in a forest and suddenly got stuck in a swamp. There was no help, hence he grabbed the straps of his boots and pulled himself out of the swamp. In a similar way, the particles mutually pulled themselves out of the swamp of particles. But finally, field theory came back. Next slide. QCD this was the previous.
This was the next one. We can go to the
yes,
one after. Oh.
In QCD is a field theory, and field theories came back. It developed in two phases. The first phase involved the discovery of quarks, and the second phase specified the nature of the interactions. So I would like to begin with quarks. These were postulated independently and practically at the same time by Murray Gell-Mann and George Zweig. Both suggested that the proton could be made up from 3 constituent quarks. These were called quarks by Gell-Mann and aces by Zweig. Their fate was rather different. Gell-Mann published the paper. First, he sent it to Physref Letters, which is the most prestigious journal at that time, but it was rejected. And then he sent it to Physics Letters, a European journal, and they accepted it. George Zweig was working in the CERN theory department at that time. CERN is a high-energy lab in Switzerland, a European lab, very famous, and he worked there in the theory department. And when people in the theory department wanted to publish something, this had to be acknowledged by the division leader of the theory division. And the division leader said, no, that is nonsense, this will not be published. And the paper of George Zweig was never published. Gell-Mann got the Nobel Prize, and George Zweig had difficulties to get a good job. But he finally succeeded. The reason that people were skeptical is the following. Next slide, please. Here, the so-called mesons are made of a quark and an antiquark. That antiparticles exist, this was known since the discovery of the positron, the antiparticle of the electron. So there were 3 different quarks, 3 different antiquarks. So one could, with 1 quark and 1 antiquark, one can make 9 different mesons, and this is, and on the left you see 1 family of mesons, and then these mesons can be excited, then they are short-lived, and on the right there are short-lived excitations of the same quark-antiquark system. Next slide. And proton and neutron consist of 3 quarks, and 3 times 3 times 3 gives totally 71 particles. So 1 octet and 1 decuplet, as they call them. These are families, and here the problem is in this line, the delta plus plus, that exists of 3 particles of 3 quarks of the same time, so-called U-quarks, up-quarks called. 3 identical quarks in 1 particle without orbital excitation, that is forbidden by a principle, the Pauli principle. This cannot happen, and that was a real problem. On the other hand, there was a triumph. In the scheme, there was this particle in red predicted, and indeed it was found in the same year as predicted. So there was a triumph of SO3, but a problem. The problem was 3 identical particles. Next slide. Wolfgang Pauli had stated that that is forbidden, 3 particles in the same state, 3 identical. And Robert Oppenheim expressed the believing at that time. He said for the quark theory, it is a beautiful theory, but I don't believe one word of it. By the way, Robert Oppenheim was known for his leading role in the development of the nuclear bomb. Oskar Greenberg found a formal solution how this could be managed. He said, oh, well, in maybe the U quark can show up in 3 different species. Let's name them red, green, blue. Then they are different, and different particles can be at the same place. So in this way, he escaped the conclusion of Pauli that that is not possible.
Sorry for jumping in here, but I just have one question.
Yeah.
Do you know the rationale why 3 constituents were postulated to begin with for a proton? What is it that made physicists postulate that there would be 3 building blocks for this to begin with?
Can you go back with the slide, please? This was this scheme. This is group theory, how it is called. If you have 3 times 3 times 3, then you get a group theoretical transition. You expect a singlet, 2 octets, and a decuplet of similar particles. Which these particles have all the same spin. The quark has a spin 1/2, and here the 3 spins add up to 1/2. So one particle and an antiparticle are up, one up, and another quark spin down, and the third one up again gives spin 1/2. In the delta, or the sigma star, psi star, all 3 spins are up. This scheme was developed before the quark were proposed. And then there was the question, what is 3? What is that 3? These red particles, these were known. But that looks as if one could make them up from these 3 particles. But there were no particles known. But then there was the question, can one identify these with particles? And that was what Gell-Mann and George Strike did. They identified these 3 with a particle and said, okay, that is the most elementary thing to get the observed octet and decuplet. And from this equation, it was postulated that there are 3 quarks with, that is then a bit numerics, with charges which are 2/3 and 1/3, but that is numerics. There I don't think we need to go into detail.
Understood. Thanks for the clarification. So then back to the colors.
Yeah. So, and at the next slide, then there was a question, do these quarks really exist? And Kendall, Friedman, and Taylor got a Nobel Prize for the experiment. If you imagine that you have a soup and you have a gun and you shoot with your gun through the soup. Well, there will be a splash, but otherwise the soup will remain intact. Now, assume you take a piece of wood and you then hard pieces will come out. Or maybe that is not a good example. Or instead of a soup, you take many tennis balls, which are in a balloon, and then you throw another tennis ball on it. Then it will kick out one ball. The soup will just make the tennis ball slower. So they did the same with electrons shooting on protons with high energy. And then they noticed that these electrons sometimes were backscattered from a soup. If the proton is an evenly distributed mass distribution, it has a size, and if the mass distribution is uniform, nothing will happen. The electrons will go through and will be scattered a bit. But if there are point-light particles inside, they can be scattered, hit this particle right, and be backscattered. That is completely impossible if there is a homogeneous mass distribution in the proton. So they showed experimentally inside of the proton there are partons, as people call them, to say if these are quarks. This we do not know yet. But these are there are particles inside with very small extension. Next slide, please. And that was the moment when people developed quantum chromodynamics. I have already mentioned Harald Fritsch and Gell-Mann, who proposed this, that the color which was needed to get the symmetry right, to get the Pauli principle, to overcome the Pauli principle, they said this color is a charge. This is the charge of strong interaction. The electric charge is responsible for the electromagnetic interaction, and the color is responsible for the strong interaction. And then they said there are three colors. That was blue, green, red. And the three colors, if you combine them, this gives white. And they postulated that particles can only be observed if they are white. A quark, a red quark, can combine with an anti-red antiquark. Red and anti-red gives white, or red, green, blue gives white. And then this color, which was introduced to overcome the Pauli principle, becomes the source of the strong interaction. And very shortly later, Wilczek, Politzer and Gross formulated a theory. These three gentlemen had already formulated a theory, and they proved that this theory indeed leads to confinement, as we say, and at large separation, the force comes so strong that the quark cannot leave. And so, and at short distances, the interaction can be weaker, and can be treated perturbatively. That was the birth of quantum chromodynamics, of the theory of strong interaction as interaction between colored quarks. The interaction is mediated by gluons, just like the electromagnetic interaction is mediated by photons. There is one big difference between photons and gluons. Photons do not interact. Otherwise, we couldn't see us, because there are transversing from the side. There are other photons. Photons go from here to here, from here to here, and they do not interact. If they would scatter, I couldn't see the screen. This interaction of this F are the fields of the gluons, and the gluon fields interact among themselves. And this leads to the existence of glue balls, of bound states of gluons. They interact and can be bound, attract each other and can be bound. This term is very similar to the quantum electrodynamics. This is the so-called Lagrangian, and I do not wish to bother you with mathematics. I just say this simple equation is the quantum chromodynamics, and this is a very simple, beautiful equation, and this has an extremely rich phenomenology. And now I go through a bit through the phenomenology. These are often difficult things, and I can only sketch them a little bit. Maybe Niklas, you can ask from time to time, but maybe we go on.
Okay.
This is again how theorists imagine this line, this solid line, is a quark and here an antiquark, and they annihilate into a gluon. Here there's an interaction of a gluon with the particle, and here are 3 gluons and 4 gluons interacting. That is these latter 2 diagrams are specific for quantum chromodynamics in contrast to quantum electrodynamics. And here you see a nuclear, a proton with a red, green and blue quark, and an anti-nucleon with an anti-blue, anti-red and anti-green quark. And if you superimpose these 3 colors, you get white. And likewise, in the for mesons, you have a red anti-red, green anti-green, or blue anti-blue. Next, please. This, just as a reminder, QCD was not anonymously accepted at that time. This is one of the rather late papers where QCD was questions, and this was a presentation, a discussion in form of a theater at an international school where students are invited and professors are invited, postdocs are invited, and they presented arguments in favor or against quantum chromodynamics.
Mhm.
However, next slide, the breakthrough for the quark model was finally the discovery of the so-called J-psi particle. This was, so far we had 3 quarks. That was a new quark, and in contrast to the system with light quarks, this system with heavy quarks gave rather stable, comparatively stable resonances, and one could see really that the quark, antiquark, the C-quark, C-antiquark system formed atom-like systems like the hydrogen atom. Very similar the spectrum as the hydrogen spectrum, and that convinced people, yes, quark must exist. Yes, please. Then there was also photons. Here this is electron and positron. They annihilate and recreate an electron and positron, and then they can emit a photon. This is called Bremsstrahlung, and that was a well-known process. Now, this should also be possible in QCD. When these are quark-antiquark, these should also be able to emit a gluon. Well, these gluons, they carry color, so they do not appear in the detector as gluon, but they get quark-antiquark pairs out of this vacuum, but they form what is called a third jet. This is an event. Here you see the actual data taken at the Deutsche Elektronensynchrotron in DESY in Hamburg. Electron and positron collide, and comes out one jet of hadron particles, of pions, mostly pions, another jet of pions, and a third jet of pions. And this can be understood by assuming that this elementary process has taken place. A quark, which hadronizes, as one says, an antiquark that hadronizes, and a gluon that hadronizes. Hadronizes mean they turn into observable hadrons, which are all individually color neutral. That was, and Madame Wu was one of the contributors, and she was the discovery as a young postdoc at DESY at that time. Next, please. Now, more quarks have been discovered, and these are called up, down, charm, up, down, charm, strange, top, bottom, and the antiparticles. And then there are so-called leptons, electron, and the neutrino, muon, and the neutrino, tau, neutrino. And then there are the particles which carry the interaction, the 8 different gluons combinations, the photon, W, Z for the for the weak interaction, and the Higgs particle for which you have heard in the newspapers. Thank you. So QCD as theory of strong interaction was created 50 years ago, and a rich phenomenology emerges. It was a theory that needed to be tested, and now it is an indispensable tool to interpret data. Now, I have prepared some special, these are now scientific contributions to the review on quantum chromodynamics, and these are, of course, highly specialized. So I just say quarks and gluons couple with the coupling constant, gluons couple with the coupling constant, and this is the point, this point in the middle, which is given by theory, and these are measurement, and the measurements agree, are precisely coincide with the prediction. Next.
And the prediction in this case is for the coupling constant, or what is it that these experiments are trying?
The coupling constants, gluon quark and gluon gluon. These are here and here, and these are different measurements which constrain this coupling constants, and one is a linear correlation, and here this is a so-called error ellipse, but it isn't worthwhile to really for the audience to understand the mathematics. This gives the strong interaction coupling constant. It is called a constant, and you see it is by far not a constant. At very low energies, it explodes, and that is the reason why the quarks cannot come out. The further they come out, the stronger the force. Here, the force between two quarks is a ton. They cannot come out. And it increases. On the other hand, in high energy physics, the coupling constant gets smaller and smaller, and here you can really do calculations. And that is very important for the high energy physics. Next. This is a graph which is nowadays always shown in lectures on particle physics. This is the ratio when you have electron-positron annihilating into hadrons or into electron-positron again. Then this ratio is given by the charge ratio, and here you can directly see that you have here the charge ratios, and you need a factor 3 due to this fact that you have 3 colors. Here's the color factor. You cannot understand this ratio without the color factor, and for that this was historically very important. Next. A large role in the physics community nowadays plays the quark-gluon plasma. In the very early stage of the universe, shortly after the Big Bang, there was an extremely dense matter. All matter of the universe was in an extremely small region, and that was extremely hot. And now people try to simulate this in accelerators. They take lead nuclei and lead nuclei and shoot them with extremely high energy onto each other, and then they penetrate. And since due to the high energy, they deeply penetrate and a very dense gas of protons and neutrons develops, and this goes over the proton and neutron. They're so dense that they dissolve, and you get a soup of quarks and gluons, and this is called a plasma, a quark-gluon plasma. And the study of this is extremely important, and these are contributors in the review who wrote on this. Yeah, next. Jepside suppression is Samin. Next one is. You all have known of the Higgs particle, which gives mass to all other particles via coupling. It couples strongly to heavy particles and weakly to light particles. And here you see that indeed the coupling constant and the mass of the particle are related on a double logarithmic scale. Here are the heaviest particles and here are the lightest particles, and the coupling constant to the Higgs particle is measured over an extremely wide range and confirms the theory of the coupling. The Higgs production occurs via two gluons and this top ring. This is a top quark because the Higgs couples strongly to heavy particles. You need a heavy particle to create a Higgs. And in this diagram, you can get from the primary light gluon to heavy particles, which then couple to the Higgs. Without gluons, the Higgs particle would have been very difficult to discover. Next.
Mm-hmm.
And this shows the complicated pattern in the high energy physics. There are extremely many particles, and the theoretical study how this is made is that requires different methods, perturbative measurements or calculations more precisely in the inner part, and phenomenological descriptions at the outer part, and these are described in the review. Yeah, next. Inside of the proton there are the spins, and the proton is really investigated up to extremely detail. This is, for instance, the spin structure of the proton. These are magnetic lines inside, and all this comes from scattering experiments. And so now a much deeper understanding of the structure of the proton has been reached. The magnetic moment was originally understood as by the assumption the proton dissociates into a neutron and a pi minus, and that circulates around the proton and the neutron, and that gives the magnetic moment. Circular currents give magnetic moments, and in the quark model it was assigned to the quark spins. All this is right, but now a much deeper understanding has been reached. Next. And a large community of physicists studies these hydrogen atom-like systems in the CC bar and bottom-antibottom system. These are the spectra, and you see you have beautiful spectrum, and this is a lot of fun of those who do it, and many unexpected phenomena are observed and need to be explained and understood. And these are two theoreticians, Nora Brambilla and Papagalu, who presented the field. Yeah. And as I mentioned, many surprises have been seen in this spectrum. Yeah. And finally, physics can also be tested if that is right, or if some physics is missing, if there is physics beyond what we know at present, by extremely precise measurements. And these are extremely precise measurements, and in these measurements the precision comes because the so-called magnetic moment, the dipole magnet of the muon, of elementary particle, depends on the exchange currents which come here from, which are exchanged here in the interaction with an external field. And these, if the precision is very high, one tests these exchange currents to extremely high energies, even higher than one can get today in laboratories. So these precision experiments are also an important tool to look if there is physics which is unhidden so far. And many people are contributing to these precision experiments. Okay. And I would say that is, I think, the last transparencies I should show. I have mentioned blue balls, and these blue balls have been predicted, and these are different calculations, and this is what I mentioned at the beginning. We finally found this glue ball compatible with the calculations, and that was the initiative to write this, or to edit this review on quantum chromodynamics on the theory of strong interactions.
Okay, very good. So in terms of final questions, I know we're slightly over time now, so I'll let you go in just a minute, but I would just like to know, as a final concluding question, what parts, if any, of QCD are still being expanded upon? If there are any areas within QCD, any sub-areas that you would recommend people check out if they're interested in ongoing process to expand our current understanding of this framework?
I think QCD is an established theory, and it is today not really tested, but its consequences are not understood. And there are many fields where new phenomena show up, which are unexpected, and which then lead to a better understanding of what quantum chromodynamics implies.
Mm-hmm.
There are many surprises, but there is no hint that QCD could be wrong.
Mm-hmm. And in terms of those fields of applications that we do not understand yet, do you have a couple of examples that you think are interesting where we're currently making headway?
There are different fields. In
Mm-hmm.
high energy field, in high energy physics, one looks for new interactions which are not known. There are predictions of new particles, so-called quarks with S supersymmetric particles, which should occur at a higher mass, and people are searching for hints for these. This is the high energy physics, the highest part. For that purpose, these are searched for in hadron machines. So QCD is the underlying theory and needs to be understood very precisely to interpret the data. So QCD is used as a service machinery to understand, so to speak, the background, in order to get what one wants, namely physics beyond QCD, beyond the standard model with the electroweak interaction, and that is the field of extremely high energy physics.
Mm.
What I would call particle physics, there at present the highest interest is in new particles which have been found, new resonances in the field of the Chabonium sector and BB bar sector. New particles are there found with funny properties, and to find these particles, to identify them, to measure their properties, that is the business of experimental physics, and theoreticians try to understand what this means, how this can be understood within QCD.
Mm-hmm.
Personally, I work on low energy hadron physics. I've mentioned blue balls. There's just one known. There should be many more. This is interesting. Then there are other forms mixed of gluons and the mesons, so-called hybrid mesons or hybrid baryons. These are highly interesting, and people look hard for these. And in hybrids, I think there is one very good candidate, and blue balls there's one good candidate, but one expects many more. So this is also a very interesting field.
Okay, very good. Then I will leave it here. Thank you very much for the presentation. I enjoyed listening to it. And
the opportunity. Goodbye, yes.